second part in our series in pre-layout considerations. And what I'm going to do is I'm going to just jump right in because we got a number of slides to cover and to discuss here today. So let's get this going here. All right, what I'm going to be covering here in our syllabus is three things. I'm going to be talking quite a bit about documentation. I'm also going to talk about schematic etiquette. The reason I call it schematic etiquette because there's really no hard and fast rules. There are obviously specifications. However, we'll call it etiquette because these are the kind of things that you want to do in order to make them very readable, and we'll go into a lot of detail about that. We'll also go into some library considerations. I'm going to call it a primer just because of the amount of slides and the amount of time that we have. I won't be able to go into it as deep as I would like to have, but we've already discussed it here, and that's already going to be June's webinar because we want to definitely spend a considerable amount of time both in the symbols and in the footprint libraries so that you can build parts that will definitely be DFM related. But we will touch on some of those things here today as well. All right, and we'll go over here to some just quick housekeeping notes. Just due to the number of attendees, unfortunately, we can't open the phone lines. However, you do have a questions box on your panel. Feel free to click on that. My colleague Jeff Condit is also online here, and he'll be trying to answer these questions in real time, depending on the complexity of the question. I may or may not have some time to ask questions or answer questions at the very end of the presentation today, so we just want to make sure that if you do have questions that we do try to answer them within the webinar itself. All right. Some brief reading material. You may have seen this in the last presentation, but I do want to emphasize this again. Don't try to reinvent the wheel. Try to use the standards where and if you can, especially the IPC and the IEEE. The other three that are listed are very good for layout considerations. However, since we're talking about pre-layout considerations, the IPC and the IEEE are going to be the two organizations that are going to have stuff that's very specific to schematics. We can't cover everything in one particular hour. I wish we could. I've tried. I keep having to pull out slides because there's just so much great material here. So therefore, definitely seek guidance from your contract manufacturers, your fab house, and your assembly house. They're more than happy to assist you up front. It's easier to work with them at the beginning than to try to get it through at the last moment. The second thing, too, is that if you're new to the industry or you're new to this type of concept of design for manufacturing, please do talk to your experienced engineers if you've got them there. Everybody learns kind of the hard way when it comes to DFM. The mistakes that you make are the learning experiences for the next project. And then lastly, if you're still looking for additional assistance, we at 9.Connects are more than happy to assist you with that. There are some consulting services that we provide. We obviously provide layout services, but we also provide quite a bit of consulting services for design for manufacturing. So if you'd like us to review your layouts for fabrication or assembly concerns, we can certainly do that. For schematics, specifically for DFM and particular for design for test, DFT, we can look at your schematics to make sure that it'll be testable towards the end when you're trying to get this thing out the door. We can assist in specification writing, which we'll talk about quite a bit today. And we can also assist in the manufacturing documentation towards the end. So when you're trying to get everything bundled up and over to your CM or your fab house, your assembly house, we can assist with that as well. We can also assist in library concepts for DFM. So if you're in any need of this type of assistance, we're more than happy to help you out in that particular area. All right, one other thing I'll mention is that we are also the value-added reseller for a company called Downstream Technologies. We have done webinars with them in the past. This is not documentation for specifications towards the beginning, but this is a great documentation tool if you're just trying to get everything bundled up and you're always trying to get it to look and feel the same way as all your other projects. This is definitely a tool to take a look at. There's a 2-minute video that we created for this. The YouTube link is over here. Obviously, we can provide this to you afterwards, or if you just go on YouTube, you should be able to find it, or to our website, you can find it there as well. So that's kind of our, I'll call it our sales pitch, but let's get on to the good stuff over here. So pre-layout considerations. There are 2 points that I'd like you to remember as we're going through all of this, and you can see a lot of slides, but these are the overall view of things. First and foremost, design work has a very profound impact on the future effort, and it impacts your layout, your assembly, your fabrication, your test, and your software. Now, if you're one of those engineers that takes things from cradle to grave, that makes perfect sense to you. If you're working in a larger organization, what I see quite often is this, what I'll call siloed effect. You're worried about what comes into your organization and what immediately goes out from your organization, and you may not see the whole picture down the line. But when you're doing design, and that's the whole concept of design for manufacturing, is that you've got to think of all these things in the design itself. It goes beyond just creating a net list for the PCB. Okay? So we're thinking about layout, we're thinking about all these other things that are going to be happening far down the line. And as a subsequent action of that, what I find quite often is that problems manifest themselves when theory becomes reality. You may have noticed, especially if you're assuming that everything always kind of falls apart at the end or unravels at the end, that initially the project was going great guns. The schematic was going really quick, the layout was going really quick, and then all of a sudden it seems like the wheels fell off and everything's spinning out of control. Well, what happened? Well, what I've seen in both, I've seen both the PCB side and I've seen the silicon side of things. What happens is that when we take that theory, because everything we do up to the point of some type of manufacturing is all theory, and we're trying to put it into a material. We're trying to make it into reality, and that's where all the problems begin. So that's why the design is so important up front, that we not just think about how we're going to connect from point A to point B, or just the functionality between those two components, but the whole design and who gets impacted by us putting these things together. All right, let's talk about documentation. I know engineers dread documentation. I'm not a big fan of it as myself, but the fact of the matter is documentation plays a huge role. And when I look back, I worked in the defense industry for 4 years in my career, and during that time I worked on probably about a dozen projects. And someone asked me at one point what projects I liked to work on, which projects I didn't like to work on. And it really came down to those projects that we actually sat down and spent the time to write some documentation on went really as smooth as glass. It may have taken us a little bit longer in the start to get things rolling, but in the end it saved a tremendous amount of time. Whereas those projects where we just jumped in and we were trying to get something done and we had no documentation whatsoever went on forever. And in many cases it just went on until the money ran out. And that's not a good way to run a project. So that's what I've seen, is that documentation plays a huge role in any project, whether it's a single board or a complete system. You want to think about documentation. Now, does it have to be as formal as the military? The answer is definitively no. But any type of documentation means that you're communicating to other people. There are three aspects of documentation. One of them is the architectural design, and this is really just this high-level concept. It's basically blocks, it's simple drawings. The second part is specification, and we'll also talk about this concept of verification as well. This is where I spent a lot of time because I was in the test and integration group at this defense firm, and most of the time when we were writing requirements, we had to write the validation method as fast as we wrote the requirements. So we were actually, in essence, writing the test plan as we were writing the requirements. And as for the test plan, it does need to be started. It doesn't have to be finished up front, but it really does need to be started. In my career, it seems like I always end up in a test group. Even though I'm doing some level of design, I always seem to end up on a test group. So I know firsthand the need for this concept of DFT, design for test. And I see what happens when we don't have design for test in products. They really cost millions of dollars in lost time and revenue issues, especially when it comes to military projects, when that DFT was not considered up front, because the designers weren't worried about that. They were worried about just their functionality. So whether, again, you're doing an entire system or you're doing a single board, these three things over here can make that project go very smooth. So let's talk about the architectural design first. Architectural design is just drawing blocks, and it's as simple as that. You take a white marker board and you start putting blocks on there. The other thing about documentation, which I think is really important as well, you don't have to do this by yourself. You shouldn't have to sit there and try to draw the stuff up by yourself unless you truly are a one-man band. You get your colleagues together, put things up on the board, and better yet, if it's a really large system, get the other people involved in it too, because they do have some input. They don't have to be in every session up front, but if you ask them to come in there and give them and have their input over there, you can save yourself a lot of problems. A lot of times that I find, especially since I'm an electrical engineer and I've worked in electrical engineering firms, the electrical engineers get together and they're the ones who start the project, but they tend to leave out the mechanical guys, they leave out the layout guys, they leave out the test guys, they leave out the software guys. And then as a result, the electrical stuff is great, but everything else suffers due to that. So when you're starting these things, get everybody involved. You can have what I call the meeting of the minds. But when you're starting this off, start it off as nothing more than a bunch of blocks. And what I wanted to show you over here is I drew this up in about 15 minutes just to show that it's not that hard to do. What I did was have an alarm clock radio sitting next to my office. And I said, okay, well, let me write this up as if I was going to create something of this nature. And I was able to just kind of do pen and paper type of thing here, saying, well, here are all the features I'd want. It says, here's my user I/O, and this is what I want in the display. And then based on the general concepts, I didn't open it up, I didn't build the thing, but I could say, well, there's probably some type of controller board over here, and it seems to have a battery backup, so there's some type of memory in it. There seems to be a radio in this thing, so there's obviously some radio circuit, and so on and so forth. So what you're seeing over here is just a general concept. I'm not worried right now is what chip am I going to use? Am I going to use one from Epson? Am I going to use one from Seiko? I don't know yet. So as you're starting this off, you start off coarse, where my cursor is, start coarse, and then ultimately you'll end up with something nice and fine. Here's a really great example of one here. This came from a Tektronix 1987 manual. It's a service manual. And I'm looking at this, and I can read this over 25 years later. It's almost a 30-year-old document. I can read this document. And it probably started off as nothing more than a bunch of big scribbled off blocks. And over time, they got it all formalized, and they were able to put this thing together so you can read it. I can see I can see where things are coming in. I see the general logic over here, and I see at the end it's going to be put out onto a screen. And on page 2 over here, I can even tell where there's buses. I can tell where the buses are. I see the arrows, so I know where things are going. Does it have to be this exact? The answer is no. But the point I'm trying to bring out is that when you start drawing out the blocks, you start getting a better picture of where things are going to go, because the schematics are going to follow these blocks, and the layout in a physical sense will follow these blocks as well. So this is where I'd recommend that you take your start when you're doing documentation. Just draw it out. I'm going to drop back 2 over here because I want to mention one thing about the white marker board. As far as I'm concerned, that is a gift to the systems engineers. Anybody who's doing this here, use a white marker board. I really wish I had done this when I was working in the industry. I used to draw these things formally. I'd do it in Visio. I had to do it for VHDL. I'd write my VHDL, and then I had to draw my blocks out. And sure enough, someone would come back, and we would have to change it. And I had to probably change it 4 or 5 times, and it was very tedious. But with a white marker board, you can have multiple people with a marker in their pens. It's easy enough to erase. It's easy enough to change. It's easy enough to take a picture of it. And I wish I had thought about that when I was working in the industry at the time, because I would have probably purchased a white marker board and dragged it into every meeting so that everybody could work on it. And when I was done, I could do a final drawing rather than constantly, do you like this one? Nope. Okay, I'll go back. Do you like this one? Nope. 5 times in 3 weeks. After a while, it gets kind of old. Okay. And so that's my first point over here, is just don't try to draw the final until there's a group consensus. And then if possible, when you are doing the group consensus here, you can use your EDA tool to draw it, because it might be able to build something off of it. So for example, for those Altium users out there, if you were to draw this on this top level here using harnesses and your sheet entries here, Altium does have a command that you could do saying, hey, make these schematics for me and put these ports in there, so it'll be able to link it up. If you wish to do it that way, you don't have to, but just to let you know that you could go from a architectural design into your schematics pretty readily in Altium if you want to do it. And by the way, as a side note, some of the defense firms out there actually use Altium. Their systems engineers actually use Altium, even though they're doing an entire system. They'll do it just because it's an easy tool to draw in. All right, a couple of other things. Let's go over to specifications. So specifications, there's 2 things I want you to consider when you're doing it, and then we'll get into the nitty-gritty of a specification. First and foremost, the concept of a spares philosophy. So when you're starting off with this, obviously you probably have in mind a level of power that you need to use, a level of the number of buses you need to use, a level of the amount of memory that you're going to want to have. But you want to build margin into this design, because number one, you don't necessarily know if you've got enough. So you don't want to build it just enough. You want to actually add a little bit extra in. Later on, you might be able to remove it. Later on, you might be able to use it for something else. But you want to build margin into the design from the very start. The second part is this concept of desirable but not required. So what do we mean by that? So if you're building something for a customer and you realize that, you know what, that a few extra product enhancements that they didn't ask for, this could be used for a potentially larger market, then put it in there, right? Because it's something that you can sell later on to a larger market and make some revenue off of it. The same thing with the foundation for design, reuse, and efficiency. If there's, like, say, for instance, a regulator that you always want to use and you know it's going to always work, and this particular design is going to work just fine for your power, then always reuse it. Why reinvent the wheel? It's going to save some time. And if there's something that you're building here which says, well, you know what, we built it for this product A, but product C over here would greatly be enhanced if we use this in there as well, you could use that as well. So that's the concept of desirable but not required. But there is a trade-off there between wanting to do it because it's a cool bell and whistle and doing it because this could actually lead to another revenue-generating product. Verification method, or pardon me, yeah, specification, the verification method. So there's three things that I want you to kind of note over here. This is an example I took off. This is from the Department of Transit, the federal government level. Obviously, they're going to do things in a more formal approach. Do you need to do it to this degree? The answer is probably not. I think that these requirements are kind of written more so than what they need to be, but nevertheless, it's an idea here. They've got what's called a tracing or a tracking number. You can or don't need to put them if you don't need them. If you're doing a lot of requirements, you're doing a big system, you'll probably need them. There's the requirement itself, but more importantly, what they're also showing you is the verification method. And this is where I want to go into a little more detail. You got a requirement, talk about how to write the requirement, but immediately thereafter, and this is why you want to talk about this in a group, is you want to declare how are we going to test this. And if you build a requirement with the thought in the back of your mind, how we're going to test this, you're going to already write two documents. You're going to write your specification, and you're practically going to write your test plan as well, at least the beginnings of it. So start with the two-column list, the requirement and the verification method. And as I mentioned over here, you're trying to write the requirement right from the start, not only in terms of timing, but also doing it correct, and then determine how it would be tested. So let's talk about requirements themselves, because if you think about it, a specification is nothing more than a glorified list of requirements. In fact, it's really boring to read. It's not there as a readable type of thing necessarily, unless you can tolerate something of that nature. But really, what is it doing? It's just listing all those things that we expect to be done, and those things and how those things are going to be tested. And shoot, if you wanted to put another column in there, you can have a checklist to say yes, it was done, because again, it's a glorified list. So what does the requirement itself have to be? Number one, it has to be concise, easily understood, complete expression, non-ambiguous, only one possible interpretation. So if I go back to my alarm clock example and I say, this alarm clock shall operate using a 5-volt power supply, okay, that's a very precise, concise statement over there. There's no ambiguity to it. You know exactly what it's supposed to, what voltage it's supposed to operate off of. So if I find a part that's 1.5 volts, obviously I'm going to have some problems with that. The other thing is got to be correct to begin with, so you don't want to have any errors, because if there's a fundamental flaw in your requirements, then obviously that's going to propagate down to the bigger project itself. It's like you were pouring a foundation with concrete and somehow you switched it with a bag of sand. Obviously you're going to have some problems with the foundation if that was all you're trying to pour the forms with. All right, consistent, no conflicts between individual requirements. So for example, and this happens quite often with larger requirements, is you'll say one thing one area and the other area kind of contradicts itself. So let's say, for instance, you don't know which pick you're going to use, and you say in one area the pick 16 will do X, Y, and Z. And then later on you say the pick 18 will do A, B, and C. Well, wait a minute, do you literally have a pick 18 and a pick 16? Or you haven't picked which one you want there, and there's a requirement conflict. Okay, so there's an example there. Requirements should complement each other. So for example, let's say the pick is going to use an I2C bus with the certain signals that are going to go out on those. Then later on, let's say you have an A to D converter, and it also has an I2C bus, and it's going to receive those signals. Well, those are going to be two different requirements, but they should complement each other. And then, of course, there's the idea of connectivity. So the same way we have a netlist connectivity in schematics, we should have connectivity between requirements. The other part is that there should be some type of traceability, especially if you have a very long list and multiple people are going to touch this, and if there's other departments that are going to do the testing for you. So some companies will just absolutely require it. It's just, you know, I remember working on some large aircraft stuff. I mean, they just had thousands of requirements. The only way they could possibly trace it was just by handing everybody a certain set of them, saying, okay, you're going to work on this set of requirements, go do these, and this other lab is going to work on these set of requirements. They would just have to break it down because there were just so many of them. So that's what they mean by traceable. Verifiable. There has to be what they call a method of verification. We're going to go into each one of these things here very briefly. But again, when you write the requirement, how do you verify it? And each one of these things has a connotation. It's actually an industry standard. So if you look this up on the web, you'll see what each one of these things means. But I'm going to go through each one of them here briefly. The other question is necessity. Who wants it? Is it a specification, or is it specified by the customer? Are we putting in a requirement because the customer said that they wanted this? Or is it also something by a stakeholder? Did the fab house say, look, if you're going to do this at this speed, you've got to use this material for your stack up, and by the way, you can only do X number of layers with this material. So that's why I say, is it by a stakeholder? When they're talking about a stakeholder, is it the designer? Is it the test guy? Is it the firmware guy? Is it the manufacturer? You want to get that information in. Again, this is why up front when you're doing requirements, you want to get all of their input in at the same time. Is it obtainable? Like, is it technically, the other part of here is attainable. Is it technically feasible, right? So, you know, if you watch Doctor Who and he has that thing called a TARDIS, well, I'd love to build one. I'd like to go chase him around. But is it technically feasible? And the answer is, well, probably not, or it's going to take a tremendous amount of time to do it. But technically feasible is a really key aspect of it. But on a more realistic note, I have seen requirements where I looked at it, I'm like, well, that's going to be about $250,000 worth of software, hardware in order to actually test that. Did they really mean that when they asked for that? Also within time constraints and budgets, one of the things I find in this industry is that engineering and business mix like oil and water. And when you start losing a balance between any two, it just ends up in a very problematic situation where I've seen situations where management have taken over and they see everything from a business point of view and they try to minimize the engineering of it, and that becomes extremely problematic. And I've seen the opposite end where a bunch of engineers try to start a business and they don't understand sales and marketing, so they have a really great product but they don't know how to get it out there. So when you're dealing with requirements, you always want to kind of have in the back of your mind that, am I doing something that's going to be very costly to the company? Am I doing something that we just couldn't even get out there because it's the time frame to do it in is nearly impossible? All right, requirements etiquette. Number one, just use simple words. That's why that prior example I showed you from the Department of Transit I thought was kind of overbearing because they were trying to throw a lot of stuff in there. But use simple words because you're writing it for all audiences, right? Engineers who do know the jargon, technicians who might know the jargon, the end customer who probably doesn't know the jargon over here, but they still want to see when you read the requirements that they understand what's going on with it for the most part. Also avoid a lot of the use of pronouns. That's why I put this picture over here. Either Laurel and Hardy, who's on first base, because I've not only read specifications where they're not being clear, but you also have those situations where you have conversations with people where they're not clear. I remember having conversations along the lines of, all right, well, John fixed the box. Well, I didn't know it was being fixed. What did he fix in there? Well, John went in there and he fixed one of the boards towards the end. Okay, I think I know what board that is. What did he fix? Well, he fixed the connector. Well, why did he fix the connector? And so when you're talking in terms of this and that and he and him and her and she, that becomes really problematic, not only in terms of conversation, but also in terms of requirements as well. The other side note I'll bring to that is that concept of the dangling modifier. So you've probably heard that old expression that most grammar teachers use, throw mama from the train a kiss. Well, that's a perfect example of a dangling modifier because are you throwing a kiss or are you throwing mama? And of course, in requirements, that's a problem because what are you really referring to? Because that can have a tremendous not only result on how the requirement is made, but how you're going to test it. All right, some requirements etiquette, consistent naming. If you're going to abbreviate, have an abbreviation list up front. Number two, call the same entity by the same name. It may be boring, but you know exactly what you're talking about. Again, you're really creating more of a list than something that's easy to read. It's not something like a novel. For example, if I said the alarm clock shall operate at 4.5 volts minimal, the alarm clock shall operate at a maximum of 5.5 volts maximum. The alarm clock shall have a display that is the color green. Yeah, it may be boring that the fact that every single sentence starts off with the exact same thing, but man, I know exactly what I'm talking about when I'm talking in that type of, when I'm constructing the sentences in that way or form. The other thing is that you really want to avoid the use of and or ors in your requirements. Now, a lot of times you might think to yourself, well, what about I say that the alarm clock will operate between 4.5 volts and 5.5 volts? So what's wrong with that? Isn't that a good requirement? I generally understand what you're meaning, but where the problem comes in is testing it because actually what you have are two different tests, and that's why you'd want to break that up. So instead of using it shall work between this and this, you would actually break it up saying the alarm clock will operate at 4.5 volts minimal. Now I have a test. Now I can create a test requirement for that. The second requirement will be that the alarm clock will work at 5.5 volts, and now I have another test requirement for it. So that's why they generally don't want us to use ands or ors when you're doing a requirement. When I say we, I'm talking about the defense industry. But even for your own sake and for your own ability to write a test plan, you want to try to avoid the concept of ands and ors. Again, in military stuff, the word shall always denoted a requirement. And we could use words such as will or may, which goes back to that concept of required but not, desired but not required. So it didn't denote a requirement. Avoid weak phrases and words that do not give specifics, because if I want a small motorcycle, well, someone apparently made one that was small enough for someone to actually ride it over here. So what do we mean by that? We don't want to use these words that leave it open to interpretation. We want to be very exact. Well, how small you want it? Give dimensions to it. How timely is it? You know, when I worked in defense, timely was 6 months. If you're looking for 6 weeks, that may not be the right time frame. It should be easy to use. Well, if you're an electrical engineer, it'll probably be easy to use. Is it something that you're building as a toy for a 9-year-old kid? Is it going to be easy for them to understand it? The ideal situation. What's truly the ideal situation? You got to define it. Are you talking about temperature? Are you talking about the time of day? Are you talking about sea level? Are you talking about being in the mountains? That's why these words are really weak. You want to give very, very specifics. You want to be very, very specific. Okay. Write the requirements in such a way that the test plan is easily derived from it. That was the quote that I had to put down there because it was really great. It came from my colleague Jeff here. And the question you really want to ask yourself is that can you easily derive a test from this requirement? So when I say that the minimum requirement, when I write that requirement that said the alarm clock radio shall operate at a minimum of 4.5 volts, I immediately can say to myself, I know how to test that. I'm just going to drop down the voltage meter to the power system to 4.5 volts, and I'm going to test to see if it still functions based off of that voltage level, right? So that's the idea is you want to do is you want to say, if I'm going to put this requirement out there, what would I do in order to test it, even if you're not the one testing it? Now, I told you earlier I was going to talk about verification methods. We write the requirement, gave you some tips on how to do the requirement. Let's talk about the verification methods that are involved, because after you write it, you want to put down one of the verification methods, and there's 5 of them out there. Okay, the first one is the concept of analysis. It is a predictive statement, and it can be based on mathematical models, simulations, algorithms. It also could be formulas or equations as well. I didn't add that to the list. Charts or graphs, scientific principles. And a great example of that is the maximum weight load of a bridge. That would be an analysis, right? So I love this one particular, Calvin and Hobbes. I remember when it came out because Calvin asked his dad, well, how do they know that that bridge limit is 10 tons? And he, of course, you get the answer that you'd expect from your dad when he doesn't know the answer. He says, well, they just keep driving a heavier and heavier truck on it. And then, of course, when it collapses, then they weigh the truck, and then they know to build the next time they build it, they know exactly what the weight limit is. Of course, Mom gets a little irritated with them. But this is a perfect example of we're not going to build a bridge to blow it up or to level it so we can determine its weight. We're just going to say, look, based on our understanding of scientific principles and the formulas and the equations, we can very accurately guess what the weight limit is. To guess, we're going to formulate what the weight limit is going to be, and that's going to be the concept of analysis. Verification method of demonstration. This is manipulating the system as it is intended to be used with the expected outcomes. So this sometimes gets confused with test. We'll talk about test in a moment, but this is just the actual operation of the item, and you can put instrumentation like a voltmeter on it so that if you're trying to make sure that something's not drooping in power, or if you're just trying to monitor something, you can do that, as long as the instrumentation does not interfere in any way with the operation of the system. The only reason I threw this one out here is because I could only wonder how many tries it took before the demonstration aspect worked. Right? This is a folding machine, so it takes in the paper, it prints it, it folds it up, it puts it in the envelope. So for those large companies that have to send out statements every month, this is the type of equipment they would have to buy. So I can only wonder how many times they had to go through it before they finally got this thing to work and demo it. Other verification methods is examinations, use of senses, non-destructive. Now, obviously, we probably don't use taste too much. We certainly might use smell, especially when we let the smoke out of a cap. But most of the time, it's really about looking at it through sight. But any of the 5 senses are part of examination, and even a physical manipulation is also part of examination as well. You could sometimes put that under demonstration, but in this case here, if I was looking at this bike here and I actually wanted to spin the wheel on it, which I wouldn't get very far on it, that would be considered a simple physical manipulation of it. Okay? It's just you are getting the verification by simply looking at it, and at that point you can say, no, that's not right because the tires are square, that's not what we were expecting. All right, test itself. So the difference between test and demonstration. Demonstration was just showing the functionality of it. The test is really there to push its limits, to find where you're going to stress it, you're going to break, and of course that's going to be really critical in those systems that if they fail could cause a loss of life. They basically are predefined series of inputs, data, or stimuli, and then you're going to test to see if it will produce a specific and predefined output. So here's a really great example of it. I was thinking, when I was putting this together, I always think about that weird joke that they always have out there about the FAA lending out its it's called a bird strike test, but I think people call it a chicken flinger. But the idea behind that was that the FAA does actually have this piece of equipment, and they fire off thawed chicken at the window to make sure that the window won't crack or it won't cause damage, or if it does cause damage, can the pilot safely bring the airplane down? So that's what they're doing over here. Of course, the old joke used to go that another agency that was not in aviation wanted to borrow, I think it was a train agency, and they launched this chicken against the window over there, and it just totally tore apart the entire cockpit. They call in the FAA to investigate, and the FAA declared the use of thawed chicken. So that was the punchline to it. But just anyways, the concept over here with the test over here is you have predefined series of inputs, and you want to know exactly if the output's going to come out to where you expect it to be. And the last one is the concept of certification. So there may be tests that you just simply cannot do, and you've got to do them. And they're performed by independent authorities using known scientific methods. So here's a really great example over here of if I pronounce this right, anechoic chamber. And this is one of those things that most companies may not have, but if you're trying to do some type of testing for maybe FCC or for UL, you may have to bring it to an agency that has one of these things that you can test it. So you can do it through certification. But the other four are generally done in-house. All right, so there's kind of a quick primer on the idea of documentation and what you may be able to do with it. As I mentioned before, don't try to do it by yourself. Get your colleagues together, work on it together, and you'll see that it'll take a little bit of time and a couple of meetings. But when you're done with it, you're going to have something that everybody's going to be really jazzed about working from, especially if you've invited others in from other departments, and everybody's going to have a really good game plan going forward. Let's talk about schematics. In schematics, I was thinking about this the other day, and really the short of it is that you're telling a story in your schematics. It is more than just a net list. If you really think about it, if we didn't have to do a schematic and we just went to PCB layout, then why would we bother with schematics to begin with, or why would we draw them? Because if you go to the ASIC side of things, they've given up on schematics. They don't do schematics anymore. They do everything in code, and that code is synthesized into a net list. And yeah, their placement tools will show you graphically what's going on, but on the ASIC side of things, they don't do that. So why are we doing it? Well, because we're manufacturing more than just a chip. We're manufacturing a whole functional system that has a number of components on it. So when we're doing this, it's not just the net list. We're showing the entire flow of the functionality, and we're also detailing very key points of that functionality. And we are creating this for all people to read, not just the layout guy. Obviously, the layout person is going to need it, but we are also creating for those people who are in test. Okay? We're creating this for those people who are in firmware, and we're ultimately creating for our end customers, especially if they need to do some type of servicing on it. Okay? So we're telling a story. And actually, the biggest problem I see with most schematics, to be honest with you, is that the story is there, but it's only partially told. So as we go through these slides, you're going to say to yourself, oh, okay, I see what they're saying over here. Yeah, I do that, but I could add this and make it a little easier to read. First and foremost, schematics should read like a book from left to right. We saw that example with the Tektronix one. Even though it was an architectural design, and maybe I didn't emphasize it enough, but if you look on the left side, the inputs that you would have, your switches were on the left side, and on the right side was the cathode tube, because that's the result that we were looking for. So they should read from left to right. And I'm not here to pick on Altium over here. I was looking for a good example of it, and I found the perfect example of what not to do. So here's an example that does come from one of their example designs, and they're actually going from right to left. Now, fortunately, if you have this situation, it's very quick and easy to remedy. And I'm pretty sure most tools will do this. For those Altium users, it would be a matter of just selecting this whole thing, starting to click and drag, and then hit the X key, and it'll flip it over. Now, can you do that on the PCB board? No, you don't want to do that because obviously you're going to have a symmetry issue with this. But again, with schematics, because they're dimensionless, which I'll talk about in just a moment, you can do that without any issues to it. So as a matter of fact, let's get to that slide here. I probably should put this one first. By standard and by their nature, schematics are dimensionless. So you're not supposed to draw things to any specific dimension or degree. It is a symbolic representation, all right, and the components are definitely not scaled. However, I think a lot of times we confuse the concept of dimensionless with the concept of of relative placement. So when I look at this particular example over here, all right, what I know about this is that there is a relative placement. What I mean by that is just by these things being connected to each other, I would expect that this connector here would be connected to these resistors in very close proximity on the PCB along with this capacitor. Okay, so there is connectivity and there is relative placement of the symbols to each other. And I'm going to go into a little bit more detail about this concept in a bit when we talk about bypass capacitors. The other thing too is that you want to show notes, and you can show in note functionality, what we call functionality notes. So in this example over here, it may have been obvious to you that there's a couple of pull-ups here. Well, there's a pull-up over here and there's a voltage divider over here. These are things that based on our prior experience and those things we would have learned in school, we would have known about. However, did you know that this was a USB port? And the answer is no, because there's no note to it. Okay, you may have thought it was a USB port. Maybe you kind of glimpsed something out of this, but there's no B on this. So you didn't even know what type of connector there is on this type of thing. And this is a good example of you're telling a story, but I don't know the full story. Again, going back to this concept that schematics should read like books from left to right, this is another thing that's kind of been developing over the last, I'm going to say almost the last 2 decades. When I first started in the industry in the early 90s, what I saw was a lot of dip packages. And the dip packages were easier enough because they had the pins on one side and they had the pins on the other side. And then pretty soon these quad flat packs were coming out, these FPGAs were coming out, and of course the BGAs were coming out, and they had more pins than they knew what to do with. And the idea of having just a single representation was getting too much. So one of the things they started doing is putting things on the top and the bottom. It's okay, but it moves you away from the concept of left and right. What I would do in the future with this one here is that given that there's 8 banks and a couple of extra signals, I would actually break this up into a multi-part component. And I would say, okay, each one of my banks is its own component, and anything that's above and beyond the banks I'll have as its own component, meaning it's part of the multi-part symbol. And what's nice about this, by the way, an Altium designer may not recognize this or realize this, but an Altium designer, you can move pins around. Okay, so if you have a component you actually want to move the pins around, you can double-click into it, and in the properties you can unlock the pins. And when you unlock the pins, you can move them about. Now you can't delete them and you can't add them in the schematic, but you can move them. And that's why I think it's a really good idea that instead of having this one large block where you got things going in and out all over the place, you can show this going as a flow by breaking this up into individual multi-parts. All right. Now in the schematics, we also think that everything should be of an electrical nature. And that's not necessarily true. They should be of a symbolic nature and they should be dimensionless, but that doesn't mean that they shouldn't be of an electrical nature. It's okay to put down test points for the test folks. It's okay to put down layout rules for those people who are doing the layout, or the fiducials, or the classes. For those people in mechanical, it's okay to put the mounting holes and non-footprint hardware in there. Never is it saying the schematics have got to be purely electrical. And then electrical itself, if you're doing some type of electrical work on it, wiring pads or chassis ground, how are you going to connect this up to the system? So when you're doing this, yes, point A to point B is always the important thing, and that's what's going to get the net list over from the schematic to the layout side. But again, design for manufacturing is thinking about all those processes down the line, the mechanical folks, the layout folks, the fabrication folks, the assembly folks, the firmware folks, even the marketing folks. Okay? That's what you're trying to do here with the schematic. Tell the story for everyone to hear. Now, one of the other things I'll recommend over here, which I like, is the idea of, and this was in this DT01 project that Altium provides as an example, they actually have a schematic symbol and footprint for the fiducials. And why is this useful? Because, for example, in Altium, if I do have a symbol and I push it over to the PCB side and have its footprint, I can use their tools to find things very quickly between the schematic and the PCB. So that's one major feature. The second feature is that Altium tries to stay lockstep with its net list between the schematic and the PCB. And if I just put things on the PCB without it being represented in the schematic, Altium's going to remedy that by trying to remove it from the PCB. And the only way you can remedy that is to either actually have a representation on the schematic itself, so the footprint and the symbol have correspondence, or you go into what they call project options and turn off capabilities so that it doesn't try to compare those things. But it's been saying it's just better to keep things in lockstep than to have to try to make exceptions. Up here on the top, this actually is also a component as well. It says PCB1, so that's actually its designator. So even in a library in Altium, you can have something that's nothing more than text. And the only reason they did this was that in this situation, they actually wanted the bare board to be a part of the bill of materials. So in Altium in particular, and probably some of the other tools as well, usually when I'm talking about these concepts, Altium's not usually the innovator in them. they've usually doing the same thing that the other EDA industry is doing. So if you're using other tools, I got to believe they're doing the same concept. But over here in Altium in particular, the only way you can get something in the bill of materials is it has to start off as a component in the library. So that's why they created this particular library part. But again, going back to the general concept, it's not just for electrical or just for netlist. It's for everybody down the stream. All right, let's take a look at schematics over here. The schematic concept, there's two concepts there's a new concept that has become more and more prevalent. When I started in the industry, there was really, there were two different methods. You did global or you did flat, and we always told people to stay away from global because it just got too difficult to track things. The idea behind a flat design was that whatever was done on the schematic sheet was only allowed to leave the schematic sheet to another schematic sheet if there was a port there to represent it between the two sheets. And then with the hierarchical design, and here's a great example of this over here, is that the only way these two sheets can communicate to each other is they've got to have a port sheet entry relationship to each other, and everything is, the connectivity is done through the top. Now Altium will allow you to cheat. There are ways to do it, and I'm not going to tell you how because I think it's really dangerous. But you can have these two sheets talk to each other. But that's dangerous for two reasons, or actually the main reason, is that it all has to come down to paper copies. Now if you're doing this by yourself and you've designed this and you're the one going into the lab and you've got Altium Designer on your laptop, then that's fine because Altium will be able to read the net list and you can use all its search tools to sync up between the schematic and the PCB. But if you're in a situation where you are handing off to another group and they are printing this off because A, they don't have Altium Designer, or B, they don't know the tool, okay, they're printing off paper copies. And this becomes problematic because most people are looking for net names, and if they see the net name on page 1 and they see another net name with a similar value on page 10, and they don't understand the concept of hierarchical design, and pardon me if I'm pronouncing it wrong, but if they don't understand that concept, then they may be saying, hey, we're trying to get this thing over here is supposed to talk to this thing, and it's not talking, and then find out, well, actually, that's not how they're supposed to talk. Now, it may not cause a lot of issues in terms of respins and those type of things. It may prolong the test, and it's going to cause delay. So if you are going to print this off, you want to make very specifically clear how to read these things. So whoever does print them off says, okay, I see I got to read this. Every time I find this, I got to follow this thing all the way through, go to the top sheet, see where it's going there, and then go down to the page where it's supposed to be. Okay, so that's, just be careful of this because, yes, it works great for organization on the design level. It can become a bit of a misery for those people on the test side. Let's talk about this, and we kind of saw this already, but I want to throw something at you that you may have not thought about. So as we talked about earlier before, schematic tells a story, and usually when we put down components, we put them in a close proximity to each other. Why? Because A, readability, and number 2, we want to minimize the trace length, and number 3, they're usually required by specification. But if I look at this crystal here, you can see that there's 2 capacitors that are very closely related to it, and here's its representation on the PCB board, which I would have expected. Okay, but one of the things that we seem to do, and I don't know where it came from because I used to do it as well, but it doesn't make a whole lot of sense. In the past, what we would do is we create a separate page and we would dump all our bypass capacitors all together on a single page, and that's what they did here in this particular example. So I don't blame them because I used to do this as well, but if we think about it, this is not a really good practice. So let's take this one step further. The bicap caps on this particular example are on page 9, and the crystal here was on page 8. Okay. Now, what is the issue over here? Okay, fine. These are on this page, and this is on this page. What's the big to do? Well, there's several of them. Number 1, the power is global. So now I've got to search all 16 pages for this. So where is this going to be? So I can't even use the tool to determine where the VBAT is going to be or where X crystal is going to be. All right. So now I've got to do a lot of extra searches over here. And then number 2, there's going to be points of confusion like, well, what about VBAT and VDD BAT? I see that you have something for battery here, or I think it is. And then you also have one that's called VDD battery, or BAT, I think it is. So where are these supposed to be located, and what's the relationship between this and this over here? I don't know what the value is. Is this VBAT maybe 12 volts, and they're somehow reducing this down to 5 volts, and they're just putting bicap caps over here? I don't know because I don't see the relationship to the actual circuitry itself. And then general placement. If I was the person doing the layout, I would have to go back to the designer and say, look, you gave me this circuit over here. I think that this is over here. related on this page to this crystal over here on this page. And by the way, there's actually two crystals, so I don't even know if this one's related to this one over here. But if it was, look at all the time and confusion we can remove if I just simply took this over here and put it right next to X1. End of story. I know exactly, at least, where C12 is supposed to be relative to X1. Okay. Net labels, definitely use them because they're going to help tell you a story here. So a couple of things here, for example, when you've got something that's got multiple ports to them, and these microprocessor microcontrollers allow you to configure these ports any way, shape, and form that you so see fit, well, that's great, but without having net labels, I don't know how you're using these. All right. And Altium does a pretty good job, for example, of giving a default name. It will use the template net underscore designator underscore pin number. So if E16 over here actually was going off to something but didn't have a pin, an actual net label to it, it would actually be called IC1 underscore CPA underscore E16 over here. Now, for connectivity purposes in the layout, that's great. But if I was a firmware guy and I was trying to figure out what are these ports trying to do, I'd be really remiss if I didn't have a label here. But by looking at this, I can tell that, oh, okay, these signals over here are my JTAG, and these signals over here are my LEDs. And that's great because if I'm doing some type of test, I'm doing either I'm doing firmware and or I'm doing some type of test on it and I want to blink the LEDs, I know exactly where to look to see if I'm actually toggling these things correctly. And I know where the JTAG port's coming in, so I can make sure that I set those ports up appropriately so that when the JTAG information is coming in here, it'll be converted, and then I can start blinking my various LEDs. Let's talk about schematic ports, power ports for a moment. They are global in nature. They are only for power. You don't really want to use them for clocks and resets. Now, can you in something like Altium? Yes, you can. Why should you not do that? Because there's usually a fan-out issue. You may want to put some bufferings on your clock in your resets to make sure that there's no major slew issues or just fan-out issues that come along with that type of thing. The key thing I really want to express over here is this concept of the label itself. So Altium already provides these things for you, but a lot of times we'll use something like power or VEE. In the prior example, if I click back up over here, they use VDD reg in or VDD bat. I have no clue what voltages those are. Again, from the test world, that's going to take me time and energy to try to figure out, well, what do they mean by power? What do they mean by VEE? So if we use a label that says basically the value and then AC or DC to it, you told the whole story at that point in time. Now, if it's analog, you could put underscore analog, or digital, you could put, for VDC, if it's 3.3 VDC, you could say digital to it, and that provides more information to it. But power VEE means nothing to the user because VEE could be anything, power could be anything. The other thing that I will highly caution you on is the concept of hidden pins. Hidden pins are extremely dangerous. I do not like them. I wish they would get rid of them. I know that some of the older libraries in Altium used to use them. The reason I don't like them is because when you hide hidden pins, you've got to give it some type of name. And what happens more often than not, especially with the power pins, is that you're going to guess at something and it's not going to be right because there's so many different ways to describe your power. Ground is usually GND unless you're doing a bunch of different types of ground. But when it comes to any type of voltage, everybody's got their own nomenclature for it and never matches up. The only thing you're going to get is you're going to get a message from Altium that says some hidden net pin is found. And more often than not, they're going to tell you where that pin is located. They're not going to tell you the component. They're just going to say it was either just hidden or it was hidden in ground or hidden in some type of power. And good luck finding it because if you've got 10 different nodes with these things in 20 different sheets, you're going to have to go search it out. So it's not an easy thing to find. So please don't use hidden pins. Again, you're telling a story, so why hide it? Test points. Test points are extremely important as well. I come from that DFT design for test mindset that when I'm designing, I always feel as though I'm the one who's going to test it. Sometimes I am, and sometimes I'm not. But test points are definitely required: fabrication, assembly, prototype, and testing. For fabrication, they've got it probably the easiest because they got a bare board, and all they're testing for is shorts and continuities anyway. Assembly's going to have it a lot more difficult because now it's populated. And of course, prototyping test has it even more difficult because it depends on what they're trying to debug or what they're trying to look at. So DFT has to be considered up front. All pins are not exposed. I got to be honest with you, being in the test group when BGAs first came out, everybody got excited about them. I just, like, how the hell am I supposed to test this? And And to this day, it's because of DFT that's the only way I know if you can test it. If you put one of those massive BGAs that got 1,000 pins down, and the only time I ever get to see it is in the connector itself, that makes it really hard to determine how things are working. Is the clock working? Is the reset working? What functionality is working? Which functionality is not working? The test folks are pretty savvy folks, and they'll figure out a way. But if you don't put the DFT up front, you're going to put a lot of time, weeks if not months, onto them in order to debug it. Okay? And you know what? There's a bunch of different things that you can add to these things. My favorite one is where my cursor is, this little green test point, the colored keyed one. That's my favorite one because I can always hook a probe onto it. All right? And then, by the way, later on, even if you've added these things all in here initially for your prototyping, you can do a very quick variant in Altium Designer, for example, and say, look, I don't want these test points. Get rid of them all. Easy enough to do so that you don't have to create 2 different boards. And by the way, even if you don't have this, as long as you have a through hole and an SMT pad that's got the solder mask open so that you can actually get connectivity to it, that works great as well. Okay? The idea behind this is that if someone's got to put a probe on a fine pitch lead, that's like saying, hey, take this baseball bat over here, and I've got let's say a field of tile, and they're all 2 by 2 inches, and they're very smooth. And I'm trying to put a baseball bat, and I'm going to say, leave that tip of that baseball bat exactly on that 2 by 2 inch tile, and don't move it. And good luck doing that, especially when you're trying to hit buttons or look at a display or something. You know that it's going to slide and go to the next area. So that's the idea over here too, is give yourself the ability to probe into things. And that's why it's so important in schematics that you think of DFT up front. You can do some of it in layout, and some of it will have to be done in layout because ultimately the physical aspects of it are going to play a role in that. But you want to start thinking about those things up front. Let's talk about notes for a couple of minutes. Notes. Functional notes are placed next to the area of interest. We're not talking about general notes about fabrication or those type of things. We're talking about why did you do something in here? What's the purpose of it? So if you have something that you think is of critical importance, write it down because, again, the layout guy or gal is going to look at this and they're going to say, okay, for example, there's a gap necessary for electrical isolation. Maybe you're saying, look, I know that based on the specification of this thing, I know this thing is going to make a lot of noise. I better just let the layout person know that you want to leave a bit of area around this thing so that you're not causing it to ring onto some of the lines. If there's a trace width that requires a certain width, again, you may want to not only just say that it requires it, but why? How much amperage is it going to take? So they say, okay, I better not mess with this. I better make sure that there's an adequate width on this trace so we can handle this amperage. If a component is not going to be populated, so here's an example of it over here. And then lastly, of course, the test points as well. What are you trying to test on that test point if it's not obvious? You know, sometimes you just put on a wire, okay, I've got this test point, that's great. But if that test point's there for something else, they say, what are you really testing with this? Yes, I can see that wire. I see its net label. What am I trying to get off of this thing? Am I trying to get off a specific clock? Am I trying to see if the reset is going to work a certain way? Is there a certain signal that I expect to have so many, to have a certain duty cycle on it? Whatever it is, you want to make sure that the test point is there and explained if it's not obvious. So I'm going to throw this at you here for just a moment. What's wrong with this picture? So we saw this one, the last one over here. It says do not populate. Okay, fine. If I'm a layout guy, I won't populate it, but I will have footprints. So I'll have a footprint for the cap here, and I'll have a footprint for each one of these inductors. So what's wrong with this picture? Well, we don't know why they're not populating it. And something like this actually causes more confusion than what it's worth. Why did they put this in here to begin with? If I'm not going to populate it, why don't I just get rid of it because that's just more real estate that this thing's taking up. So if I was not going to populate it, it would be very beneficial to have a note here that said, why are you not populating it? Okay. Another thing, too, that most people know about Altium is that there are these things called directives. They're basically a little stick. It looks like a lollipop. It's a little red stick with a little red circle around it. And you can put them on there either for classes, for net classes. You can put them down there also for the rules. But if you just say power, well, what does that mean? Is that a power class, or is that a rule? So you want to put more details over there. Say, look, this is for a rule for this trace width because I'm doing this amount of amperage. That's, again, telling the story. So you can see here that a lot of times we're telling half the story, but these little things that we add in there, these little extra details, tell the rest of the story. And hopefully you're seeing as we're going through all these examples that, wow, if I do that, that saves 10 minutes over here for this guy. Wow, this over here will save this guy running to me and spending an hour talking to him or her in the test group. So that's why you want to make these things thorough. That the little extra work you put up front is going to save a lot of time down the road. All right. Upon schematic completion, there's an ERC, electrical rule check. And my recommendation is that you understand what you're going to get here. Altium's going to throw a lot of stuff at you. I think all these tools will do this. They're going to throw a lot of stuff at you, and you really want to look at it because it's not prioritized necessarily. And so you want to see what's going on. Now, do I say take all these things and make them errors by default? No, because some of these things are truly warnings, and some of them I think just need to be turned off because I don't really even know why they even added it in. And by default, some of them are turned off by default because they're not really that pertinent. But what you want to do is make sure, is a warning really an error, and is an error really a warning? And a really great example here is this one called unique identifiers error. By default, it's a warning. As far as I'm concerned, that's a fatal error. The reason why is because Altium uses unique IDs for both its symbol and its footprint. So even if the designators are in the process of being back annotated and there's a time and place where they are not the same, the unique IDs keep them in sync with each other. All right, and so if my unique identifiers have errors to them, I want to remedy that as soon as possible. So there's an example of the electrical rule checker. The last thing is for design review. And even though I just put this as one step over here, make sure you actually do a design review. Have a peer review, beat up on that thing, take a look at it, make sure it's ready to go before you move on. A lot of times we're like, good, you're done, move on to the next thing, and we almost entirely skip the design review, and obviously that's going to cause problems down the road. But the design review should also look at the requirements. Did you hit these requirements? Right? That's why the requirements are important, because it's not just at the end when the product's built, it's at that stage where you're putting everything together as well in the schematics. Let me talk about libraries for a very brief moment. As I mentioned earlier on, the libraries will be, we'll talk about this more in June. I think there's a lot of things that we can show, and this right now we're just going to summarize it. As it says, the topic all its own. There's certain things you must have, and for example, a symbol and a footprint. But I can't emphasize to you enough the need for parameters, and the parameters primarily for their bill of materials. The 3D representation is also for the electrical and mechanical handoffs to each other, and I'll talk a little bit more about this one in a moment. But bill of materials, I can't emphasize to you enough that when you are done with your schematic, before you start layout, do your bill of materials. Deal with it right then and there. Because if most people will say, no, I got to move on to the layout because I got management watching me. Okay, now I got this thing pushed over to fabrication, and now I'm going to go back and look at my bill of materials. Well, there's several issues that you're probably going to come across here, which almost guarantee a respin. You may have footprint dimension issues. You could have picked a part that, yeah, this will work for your board now, but it's not going to work for you 3 months from now because it's going obsolete. Lead times are too long. I need it in 3 days. It's going to take 3 months. Cost prohibitive. You picked the wrong part. Yeah, you're building a Happy Meal toy. You put a $3,000 resistor in it because you didn't realize it was rad hard and hermetically sealed. Right? And so a good practice is that the layout doesn't start until the bill of materials is handed off to purchasing. Because even if purchasing comes back and you're midway through things, even if you're almost done routing it, and they come back saying you can't use that Xilinx part, they just declared obsolescence on it, yeah, you'll be mad. Yes, you may lose 2 weeks, but no, you didn't lose $10,000 in a respin. Okay. Okay, let's talk about footprints for a couple of moments. And again, we'll go into a lot more details about this in our next webinar. For the footprints, you need to have more than just copper LAN pads. A lot of times I look at a footprint, and that's all I see. I see maybe a little speck that represents pin 1, and then there's just 2 LAN pads, and that's it. Why do those worry me a lot? Number one, IPC naming does not mean adherence. So if someone's using an 0402, well, is it truly an IPC, or is it, does the part itself actually adhere to IPC? Because they'll say it's an 0402 part, but you've got to look at the specification. As a matter of fact, there was a company I was working with, and they let it be known that with every part that comes in, they are not going to try to pull an existing part out of their library. They will draw this thing every single time because they want to build it exactly to those specifications. Now, you might think that's overkill, but at night they sleep well knowing that that 0402 is truly an 0402 for that particular part. Okay, courtyards. Courtyards are kind of this archaic thing that we originally put in there for those people who are going to do the population of the board by hand. However, they're just as important now as they were back then. So maybe we're not using manual labor to put these things together unless they're really small quantities or very complex. But they do serve for different other purposes. For example, in layout, you can use courtyards so that you can get a very quick fit and placement on them. Right? So yeah, there are component clearance rules that you can set up, for example, in Altium, but just visually I can just tell right away if this is going to work or not. And by the way, let me give a little side note on this one. This was our original courtyard, the green one. And then we were working with a particular customer where they were having some issues getting this into their manufacturing in China. So when we went back to their manufacturer, they said, well, these are our specifications for this. And so what we did is we drew a new one, a new courtyard around based on their specification. So be careful about the courtyards in general because they may work for one organization but not work for another organization. But you definitely want to have them in there, especially for the concept of mechanical for egress. So this one is around this one particular capacitor. But on a component, I may have a situation where I actually have a latch. I want to make sure that latch can come completely down so I can disengage the connector. Okay, so I actually would have a courtyard around there to say, if I got this courtyard over here, I better not be putting other components in this area or I'm not going to get this latch to come down all the way. For assembly, you may want to have enough space in there so that BGAs that may require rework can be done. Here's an example of a piece of machinery. It just placed down. It's going to put its heat. It has this basically its tube here. It's going to blast some incredibly hot heat here to basically liquefy the solder balls of this thing so they can pull it off. But this won't work if you've got other high-profile components around it. And of course, the pick and place as well, because most of these companies will use an electronic pick and place machine. That's going to be an issue too. So you want to make sure that the pick and place can actually get its head down there so it can actually drop it in there and it's not smashing into other components. And then lastly, the idea of probing for tests. So if there's enough space between these things, you can do things with it. You know, for example, you can get a probe on top of it, not worry about it sliding off. Or sometimes if you got to do things like dead bugs or tombstoning in order to do a bypass, then with this courtyard over here, you can allow for human manipulation. Other mechanical considerations, you can define, people asked about mechanical layers. I'll talk about this more in the next webinar, but there's no standard to them, which makes it kind of frustrating. So it really comes to company policy and agreement amongst everybody to use the same mechanical layers. And then, of course, 3D bodies. This is really important, too. If your tool is capable of doing 3D bodies, use them because this bridges the ability between the electrical world and the mechanical world. A lot of people always say, how did Altium all of a sudden come onto the scene? I can tell you right now, it was because of this 3D capability that they added in back in 2008. Once you did that, they really bridged the gap, the chasm between the electrical world and the mechanical world. And then lastly, of course, you want to add mechanical dimensions. You'll have to draw them into the library, specifically in Altium, because the features or the tools that they provide on the PCB side are not found in the library as well. But as I mentioned, we'll definitely go into a lot more of these details here in the next webinar series. One last thing I was going to bring up here. This is one I was going to show last time, but I felt it was more of a library thing, so I wanted to bring this to your attention. It's very common for people to use a pad in the center over here and then connect to the ground because they want to pull away the heat from the component. And this is a noble concept, but it won't work. And the reason why this won't work is because these are basically generally they're through-hole components. And when you try to put some type of paste on this thing and you heat it up, it's going to go all wick. It's just going to wick straight down because the gravity is going to pull it through, and you're not going to make any connectivity whatsoever. So if you do want to have a pad in the middle and you want it to connect to those things that are on the plane, you got to have to be a little bit more savvy about it. Here's a great example down here where you have this pad, and then they've got the solder mask around here so it won't wick into these via holes or through-hole pads here. So they still have electrical connectivity, which in turn will provide thermal connectivity, but that solder is not going to be racing down these holes over here because it's basically barriered off by the solder mask. And you would do the same thing over here too. The difference is you may be putting 4 of these through-hole pads on the corners, maybe 6 or even how many, 4. Depends on how many you want to put over here, but the idea is that the pad itself would just be a solid pad, and you would have these things connect off through traces. And again, the solder mask will prevent these things from wicking down into the ground vias. You can obviously use plated and plugged vias, which sometimes you have to use for BGAs, which is completely understandable, but that's an expensive option, especially for something of this nature here. So with that, that's what hopefully you found this to be useful. Really appreciate you attending. I see that I've gone a couple minutes over time, so I'm not going to take any questions at this point in time. If you're interested in our slides, we'll make these available here soon enough, but please do contact your representatives so that you can receive them. And also the questions that have been coming in, I noticed that there's been a lot of them. Unfortunately, I said I won't have time to do any Q&A at this point, but we will get that question sheet typed up so that if you're interested in seeing that, we can certainly send that to you. And with that, I'm going to sign off. Thank you very much for joining us today, and we look forward to meeting with you again in a month from now.